Hi, Franz. Welcome back.
Hi again, I would say.
Yeah. We have two choices today, JCTools or I/O.
For JCTools, there is a lot of... for such a small library, there is a lot to say, to be honest.
Yeah.
And it's interesting. I/O still...
Then start with JC?
Yeah, let's do it.
Yeah. First surprise to me was that it was actually created by Mr. Click. And I had a podcast with him, and I didn't think we mentioned JCTools. So he's also hyperactive, it looks like.
Yeah, I mean, for JCTools, there is a bit of history which I'm not part of in the first part of the history of JCTools. So basically, it was a concurrency utils made by Nitzan Vackard. At that time, Nitzan was not still working for Azul. Mm-hmm. And at that time, Cliff was working in Azul. When Nitzan write a series of blog posts on how to improve the existing concurrent queues for the JVM, he brought a few very good novel ideas, and others coming from many different, languages, including C. Fastflow is one of the library that he took as an example of a good implementation for a single producer, single consumer queues. And after he wrote the blog post, a few months later, he started working with Azul. Probably he got in touch with Cliff Click. And since Cliff has created a very known in the concurrent world algorithm for a non-blocking hash map, he asked him if he could donate this to this novel library that Nitzan was working on. That has been named as JCTools later on. Mm-hmm. So the actual donation has happened when they were both working in Azul. And actually, the JCTools people became maintainer of the non-blocking hash map from Click. So we have kind of been not forced, but it was a pleasure that we had to learn how it works in order to fix if there are misuses or issues or just bugs. Mm-hmm. And it's interesting because I wasn't still into this conversation. I was an observer and actually a reader of the blog post articles from Nitzan. And I start to get interested into it because in my previous companies, we needed to perform stream processing, and Storm from Apache wasn't good enough. So we built our in-house engine. And because of that, I had to learn what was the state of art for concurrent queues, not only in the JVM. And what I discovered so far was two libraries. One was the Disruptor, and the other was JCTools. So because of that, I got interested into the internal. And I start to contribute it to both. To the Disruptor, not that much, because it wasn't fully fitting our case. But for the JCTools case, yes, it was a perfect fit because we just needed a replacement for the concurrent queues that we were using at that time. And after a few big contributions, I've been asked from Nitzan if I could be one of the author of the library together with Martin Thompson and him. And I'm very happy about it because even if it doesn't look fairly active as a project, it's because it doesn't need it. So the algorithms that are there are probably the top-notch, even currently, because I verified currently, of the algorithm to build a very fast concurrent queues in Java. And so unless you have bugs or specific feature, there is no point to keep on contributing there, unless there is something that it's required attention. But the algorithms and the ideas there are awesome. There is a lot of performance work.
Which and Apache project was it? You said there was an...
Apache Storm was
So you worked back then for Storm?
No, No, I was a user of Apache Storm in my previous company, but we found
what you
out
did with the Storm. I was always curious about the use cases for Apache Storm.
Yeah, in my case, it was similar to risk management. So we were working on a stream of events, and we had to collect in Windows if something was off because of some threshold or things like that. But in our case, we were talking about billions of events per second, and the Storm wasn't the right fit for that. So we needed to go lower level. So we built our own.
And what would be the killer use case for Apache Storm? Because I'm just curious, because we have Apache, we have Kafka, we have Flink, we have Storm, and I also was curious to know why I would use Storm.
Let's say Kafka, it's highly dependent by the disk. There is no way you can avoid it, but it gives you some good things out of it.
Yeah, Kafka I understand, but Storm, I just searching for use cases.
In memory, when you need to do everything in memory mostly for those kind of stuff. So you can.
This is like Kafka, but in memory, right? So you say
not like, but the use case you could cover could be similar, but maybe you don't need anything so fancy like having topics or entries or what else. If you need it, you can do it, but actually it's more stream processing for the most. And it just makes you able to have all the building blocks already in place in order to do it with the different types of utils. So if you want to work in time window, token window, so there are many things that you can do.
But I think now if you mention that, because Kafka can also do that with Kafka streams, there's Windows and so forth, but I think Kafka is more a database, and the Storm sounds to me like it is a transient event, right? So it doesn't make any sense, to persist a stock quotes.
Exactly. And he's not exactly. He's not interested into the part related to persistence. So he's literally like a function foo in which you put things in and you want just things out.
Okay, cool. So the first, because I heard a lot about the Storm, but I said, why I would use it? And unfortunately, I don't think there is a name for a transient and persistent event, because Kafka also deals with events, but these events is more like, it is like domain events, and they are persistent. And they are transient event, like, something happened, and if I cannot process right now, then forget it. It is only, valid for a few seconds, minutes, or whatever, and then it just doesn't make any sense to persist it. And we can call it transient event, but I don't think there is a proper name for it, right?
Yeah, considering that the fact that Kafka requires persistent as part of what it does, it means it requires encoding and decoding of things. So if you wanted to process things from Kafka without having any copy, you can't at the moment. You always have to copy something.
And there's a broken and so forth, right? So this is
So depends what are your threshold, what your SLAs. Maybe you won't fit your case, and that's exactly why moving to an in-memory kind of processing could make sense. In our case, it was fairly simple. So we needed something terribly fast, very little garbage, and in very parallel. And actually, we couldn't find anything. The Disruptor was decent in that, but later on, I discovered that JCTools could be even faster. Or better. Depends, but let's say they could be even faster. And because of that, I learned about the algorithm, the implementation tricks, all the performance background that was making JCTools as good as it is currently. And even now, recently in Quarkus, I talked with one of the maintainers of Mutiny. That is Julien Ponge, in order to leverage directly the implementation for JCTools for most of the queues that are used within Mutiny. But since in JCTools we perform some code generation in order to have different flavors of queues that have slightly different behavior or memory footprint, I had to modify very recently JCTools in order to produce unpadded variant of the same queues. Because in JCTools, since from the first day, I think, Nissan was caring a lot about having the right scalability for each one of the queues. The queues employ different performance technique to achieve it. And one of the most known one is to have to avoid false sharing for the parts that could be contended in the queue. But if you do something like that, it means that you have to add the padding around the so-called hot field that are supposed to be shared or false shared. And that makes the queue bigger in terms of memory footprint. While in Mutiny, sometimes you have to create on the fly a queue, and you use it as a channel to send messages across it. So in that case, if you have a too costly object to be allocated, even if it's just a queue, is not good. So in order to avoid this regression, we have different generator by using, I don't know if it's Java Poet or something similar, something which we can generate Java, basically, Java code. And we had a common generator to create an additional flavor of the existing queues that make them unpadded. So you still get the good things about the implementation performance aspect, but maybe you don't care that much about the scalability, and still you want to benefit to have a better algorithm if compared to what Java offer out of the box. That is rather poor, but for good reason, because it is a general purpose, let's say.
For the listeners, we are talking 10 minutes about JCTools, and what they are is Java concurrency tools. I think this is the long form, and they implement internally patterns and queues, right? You can have
counters. We have counters, maps, and queues for the most. But the queues are special. But even the map, the algorithm of the map is the one donated by Cliff, actually.
And Cliff is the inventor of the algorithm
of the map. Yes.
Incredible, actually. I have to invite him back. He never mentioned actually his algorithm, so we had a nice chat. But never about
It's super interesting because that same algorithm is being used in a lot of C and C++ video games as the reference implementation. So the people copy and pasted from the Java version. They add different reclaiming methods because one of the problem with C and C++ is that you don't have a GC. In order to get there, you have a different mechanism. And the usual one is the quiescent state reclaiming is one of the patterns used by the C++ folks. And they implemented that pattern on top of the algorithm made by Cliff. And so that algorithm was that good that actually was used literally in a lot of different other projects.
So I was on the Stone page, and they are claiming they are able to send or process million messages per second. And you told me it was not enough, and you had to go lower level and had to patch JCTools to be even more performant, right?
I invented an algorithm for that. That's different. So I actually learned what JCTools was offering, and there was a missing bit. And that missing bit was I named the queue the X8 multi-producer single consumer and multi-producer multiple consumer queues. So there are two queues actually. And these queues are, the algorithm is invented by me. And I send the implementation to the JCTools folks. And it was a good home for both the algorithm because first I needed to depend by a single library, that is JCTools. We used already few ones of these queues, but under contention, they were not good enough. So I compare against what the Disruptor was doing under contention, and it wasn't good enough as well.
So crazy. So wait a second. So you had a storm, and storm broke, or what was it consumed too much memory, or what was the result, or what you had production problems, or what was actually?
We were not able to match the SLA. The SLA was in my case literally like 100 millions of requests per second. 100. Yeah, that was actually the and it wasn't good enough because it was capable maybe of 1 or 2. So it's like 2 order of magnitude less. And we knew that Java can do it because actually the light speed is not rocket science. You know how much you can push it.
I'm laughing.
It's physical.
Years ago, I was hiding a project, and they told me they have scale like Google, and I have help to help them. And I said, okay, I was a little bit afraid. I was like, okay, what I can help? I mean, Google is Google, right? And I said, what are you processing? And I said, millions of messages. Like, okay. And then they explain what has to happen, and then ask, millions messages in what time? I mean, is it like second, minute, or whatever? And this was, I don't know, I think hour or whatever. And then I try to calculate, and I say, okay, but what this means is we have, in best case, or in worst case, like 2 to 3 transactions per second, right? And they said, yeah, you are actually right. So, and what you're saying is, millions of this is a big deal. So transactions per second with Java, right? So this is actually incredible.
Yeah, let's say that what JCTools can deliver with a single producer, single consumer scenario at the moment, since there are limits related to the speed by which the last level cache is capable to transfer data across cores, is about 400 million of messages per second if you don't do anything. And that's
how big is the message? What is the message?
It's just a single reference. So you basically pass events that maybe you already pulled somewhere, and you just send them across the queues. So the actual throughput of this is about 400 million per second. Oh, at least the last time I measured it.
And if you would use stock Java collection, how fast would it be?
I think it's 2 order of magnitude less, at least.
Million?
At least. Probably in the million ballpark. But you have a tons of garbage created, because one of the main problem with there are 2 big problems with the existing Java collection, even concurrent link queue or transfer queue or whatever. The first problem is that they are literally implementation, a very smart one, of existing algorithm on paper, which, in paper, they love to have a linearizability kind of proof. So anything that use linked nodes is very easy to prove that kind of stuff. And they are linked list, basically. And that's the problem. So you got to create new nodes every time. And that's something that in our case, it wasn't the right thing. And the other one is that you cannot benefit of any prefetching or any batching that currently you got when you work at the right level with laid out data correctly laid out in memory. So, for example, if you have a linked nodes, you always have at least 2 jumps. Now, because you have the tail of the add pointer, and you need to go to the real node and get the next, whatever it is. Conversely, if you have an array, it's simpler. The array is already there, and the next doesn't require you to go to the previous one, so you can actually prefetch it. Just don't depend by the previous one. Not having this inherent data dependency is what make it to fly, actually, and it doesn't create any garbage. So that's an additional thing. But for this reason, it means that you cannot rely on the usual mechanism of in-place nodes and the leverage the full queue API and collection API. Indeed, one of the limitations for JCTools that make it very fast is that it basically leave on the ground so it doesn't care about some of the implementation of the collection library. So it's not a full replacement in which you can actually do whatever you want, like removing in place an element. It doesn't happen. It's more a channel in which you transfer things from one side to the other, and you expect to have them in a FIFO kind of order. And that's it.
So what you're saying is that the Java's collection implementation is based on papers, and the papers usually described a linear chain of node because it was easy to reason and to prove it.
No, it's actually a proper property. So the linearizability property is a property of concurrent algorithm in which, in whatever way you can arrange the order of whatever happened, you can always prove that there is some form of, I don't know, it looks like more an interview for Adzecast, this one. No, actually, linearizability is a property that requires proofs. Mm-hmm. And with the linked nodes data structure, sometimes it's easier to find the so-called linearization point. Mm-hmm. And that's why most of these algorithms employ linked queues. The other one is that they want it to be unbounded. Mm-hmm. Because one of the main problems with the user is what happens if you make an offer to an element and you get false, you can't. Mm-hmm. It's an additional thought in the mind of user, right? So having linked queues make it unbounded, so you don't have to care about this problem. But you are just relying on the fact that you can actually create on the fly nodes.
Memory. Mm-hmm.
Exactly. In the reality, what you're going to do is to move the problem elsewhere. Because if you have to allocate nodes, it means that you can have a pool or you can have a GC or heap or whatever you want.
No back pressure, right? So
without back pressure, exactly. So when you are in this scenario, since you want to focus just on the algorithm, it's very convenient to use a linked nodes structure because you're actually just forgetting about this detail that in the real world could be very relevant, actually, because you don't know if allocating an object is always a fixed cost, and it is not actually.
So you refer to linearity. What do you mean?
Linearizability, yeah.
Yeah, what you meant was the concurrent property and not the implementation, right? So because it has to be proven, the implementation was was more straightforward to make it provable, and and the JCTools are more creative and are not implementing all the Java collection methods. They don't care. They only care about speed and no garbage, right?
Yeah. Exactly, and they have been, and still, although this lack of a feature, if compared to the normal Java collection, we have been forced in JCTools in order to still be able to have a linearizability to tie the methods to the actual expected behavior from the Java collection library, even for methods that we, in theory. So we care because we have to implement such like offer and poll, but there is a third method called isEmpty, for example. So your expectation is that when a poll is null, in theory should be empty. Mm-hmm. But this kind of behavior is decided by Java because of the queue contract, and is never relaxed when it comes to concurrency. Mm-hmm. When you are parallel. But the reality is that depending on your implementation, you could have intermediate states. These intermediate states is what break the linearizability of the isEmpty together with poll and offer. Because, for example, I can decide to have a third state called unavailable. So the offer happen in a way that is not atomic. It's made of two steps, let's say. And in that moment, when it's still transitioning between the intermediate state to the final state in which the element is actually placed in the right place in order to be drained, what happens if you call isEmpty? What happens if you call poll? isEmpty will say true or false. Because if it's an intermediate state, you can pick your poison. You can tell, okay, it's not empty, but you perform poll and you get anything because it's still not there.
It sounds like quantum computing almost.
Yeah, kind of. Because he's a giant, or he's not a giant. You try with the concurrency to keep your states very bound in terms of numbers. because it makes it easier to reason about the data structure in general with concurrency. But the reality is that the smartest algorithm can have intermediate representation that can leak till the actual interface if you don't implement it in the right way, the mapping. Because the expectation from user when they call these methods is that if I ask for is empty and I perform a poll and it's really empty, I don't want to have a null. Or the opposite. You would expect to find an actual element. And so we have been forced to do two things. We have an extended API for JCTools called Message Passing Queue that has been invented by Nitsan. And this API have additional method like relaxed poll. Relaxed poll can return null even if you are in one intermediate state. And the same happened with the relaxed offer or weak offer, because you can get false just because of too much contention. And could be very useful. The point is that depending by how much you want to rely on the existing API from the collection or the one from JCTools, you can have a new opportunity, new chances to optimize things, because you have an additional API that is not bound to spin weight until the element became visible, for example. And that's exactly what JCTools does. So in the poll method, if you are in an intermediate state in which you know that the element will be very soon visible, we spin waiting for that. And the reason we do it is because that's the API. So having another API that doesn't force us to do it actually improve performance, not because it is a smarter implementation, just because it doesn't have to be tied to what the original API forces us.
I'm just curious about the linearability. And,
linearizability.
Linear. Is it related to transaction serializability, right?
I think that there is some...
because transaction serializability means if you the order of transaction under concurrency. So if you have transactions, incoming transactions, and you have various isolation levels, the highest serializability is means serializable, looks from outside as if it were the order is always given. So it is it is always in the right order. And if you relax the serializability, you will see side effects under high pressure. So
it's definitely related. There is an actual library from JetBrains that is called LeanCheck. And LeanCheck is probably written in Kotlin. I would be surprised if it is not, but it is. And with the LeanCheck, you can verify the linearizability property that you expect from concurrent data structure. You can prove it. And if it doesn't hold, you can get the sequences that break it. So actually, you can perform actual proper tests in order to verify that that's happening correctly and is actually enforced for real. But as usual, these are runtime tests. The reality is that if you can prove it, that would be better.
Yeah.
And the more complex is the data structure, the more it's not easy to prove the so-called linearization point. So a point in which from now on you can determine that the history by which in whatever way you come at a specific sequence of state, the outcome will be always the same and this expected one.
So the linearization property means it looks like a single thread system, right?
Kind of. You can have even different order of events, but as long as they are dependent in a specific way, you expect a very specific outcome.
Okay. So this is really very similar to serialization.
It's properties. Very similar. Yeah. It's similar.
And you refer to queues in JDK. You mean the queue interface with add element, pick, poll, and remove?
Yeah. And there is an additional one that is called message passing queue, in which we implement file-less methods.
You mean in JDK or is it in JCTools?
No, in JCTools.
Okay, and because in JDK, what I just found is there's an offer and pick and add, and in the Java doc it states inserts the specified element into the queue if it is possible to do so immediately, without violating capacity restrictions, returning true upon success and throwing illegal state exception if no space is currently available. It means there is no back pressure. I mean, the back pressure is illegal state exception, and offer, this is with Boolean, is without exception, and it says insert the specific element in the queue if possible, to do so immediately without violating capacity restrictions. So it means either it does it immediately or it blocks. This would be my understanding of the behavior, right?
No, the offer should not block, actually, unless there is a variant with a time unit. I don't remember by heart, to be honest.
Because the contract says to do so immediately without violating capacity restrictions. If it is possible to do so immediately, it means it could block. This is the strange part. So if you read the Java doc from the interface, this is if you search for queue and then go to offer, the method offer. So if I read the method, it's just one sentence. So I would understand. So the contract is, it doesn't block, but if the queue is full, it will block. This is Java.
Actually, the actual implementation doesn't do it. You have to use a blocking queue for that. So there is an extension to the queue interface in which you both have take and drain. And drain is the batching variant, while take is the not batching variant that can block. And there is an additional method for offer, in which you can define for how long to block or even forever until the capacity is available. So actually, there are variation of these methods that can actually block. Mm-hmm. But if you don't implement the blocking queue interface, usually just the Q1 return pretty much immediately. Pretty much that's the problem. Because something that the people doesn't realize is that blocking is not tied by thread that block. That's the usual conception of it, but it's not correct. You can even block by spin waiting, because actually you don't make your system available to make any progress. Mm-hmm. So you are consuming CPU and not making progress. So actually is blocking. So when you have a concurrent queue, like, let me give you an example.
Exactly. What is blocking actually? I wouldn't care whether the CPU spins or not.
I know. There is a proper academic definition for that. So every type of algorithm, concurrent algorithm, relies on different progress condition. Mm-hmm. And usually when you say a lock-free algorithm, you are not saying anything about the fact that you block, but the fact that you are not using locks. So when you are...
That's an expectation, because if you read, lock-free, I would assume non-blocking, but it's not true.
No, it's not true. Yeah. Indeed, there are different other shades, let's say, of being lock-free. That depends from how many steps are required in order to make progress. So if those steps are fixed somehow, is it called wait-free? That is an additional property of being lock-free. While if you don't have a wait-free guarantees, you can even block because of contention. So since most of the most known algorithm make use of atomic instruction that can fail under contention. And one of the most common one are the so-called load and compare instructions, so the compare and set. Mm-hmm. Yeah, the compare and set instruction can fail because of contention. If that happens and you retry, you start from scratch. Mm-hmm. So you don't know when this is going to succeed. It can even take an amount of time, but you can build a concurrent algorithm that instead have a finite bound of attempt before succeeding. And the two queues that I implemented for JCTools are wait-free kind of queues. So they are special because it was what we needed in my previous job. So I needed to make sure that if I offer an element under contention, this is going to succeed in a finite amount of step. And I want to measure that step.
So almost real-time quality.
Yeah, I mean, depends by if you are happy with the number of steps that are required. But since it could be tuned, usually it was able to deliver real-time property.
So real-time for me doesn't mean fast. It means predictable, right?
Yeah, it's predictable. In this regard, yes, it is. Mm-hmm.
Okay, that's actually interesting. And what you said is it made me think right now because if you consider optimistic logs, so I'm 20 layers above you, so let's say in a database, and you have conflicts all the time. So from the user perspective, you're absolutely blocking, right? Because you have to resolve the conflict and you cannot do any progress. So I think from your perspective, it would be optimistic logs with blocks, because if it's not done properly, you are waiting until it resolves, but it never resolves, right? So
exactly. And as usual, the devil is in the detail. Depends what you mean with the progress. Because if rejecting a request doesn't allow it to happen very often, it's still progress if you think that's okay for you.
Should be on use case level, right? Progress. So it has
exactly.
to be yeah.
Exactly. It should be defined like it's part of the service level agreement. You need to define what service mean for you.
Because it would even mean that pessimistic logs are less blocking than the optimistic log.
Yeah.
That's actually a cool story. But just for my understanding, I'm just curious about the 400 million transactions per second. So I assuming there was like a network part which got the events, and there was a buffer between, and then you had to do something with it, predictions or whatever, maybe aggregations, calculations, and then throw away the events, right? This was something like this.
Yeah.
And in such environments, you would need highly performant data structures, because if you have one contention, the problem is everything will queue up in shortest amount of time, and the result would be an unbounded queue. I would say by 400 millions per second. I would say in view minutes or in view seconds out of memory.
Yeah.
How fast would it be? You had such a. I think it's just like how fast you will fill up the RAM.
I would say pretty much fast.
Yeah.
But that's why you would
right?
like to have.
This is like under a minute. Yeah.
But in that case, depends what depends. I have another patent actually that is not being implemented in the JCTools because it wasn't fitting the API of
you have patents. You have 2 patents.
I have a few patents. Yeah. One of these patents is called broadcast queue or leaky buffer queue, and is actually solving this problem. So let's say that you have a source of information which you cannot stop it because you keep on sending, but you have a finite amount of memory. So in that case, you would like to have a predictable way to offer the data without caring literally if it's going to be picked or not. So it should be not if there is no available data, I won't push it. Because if you do something like that, you place basically a branch in your auth path, and you can die because of branch misses. So you would like just to keep on offering. And I implemented a sort of a concurrent queue that allows to have a wrapping handled directly in the protocol of the queue, in a way that if you override an element, you know how many samples you just missed. So you can decide to increase it or poll more frequently. And in that way, you can find if you are able to actually sustain the stream. So there are many use cases why you don't want your memory to be bloated by element. And there are many strategies that you can use.
I have a heretical question, because in such systems, high-performance systems, where everything is optimized, do make queue even sense? Because if your consumer is highly tuned, you already know that you can process 500 let's assume 500 message per second, and your producer produces 400 message per second, never more. And this is your margin. Having queue in between is like saying, okay, it could happen in one point of time, then my consumer slows down for whatever reasons, and then I have some buffer. But if the consumer will slow down, it will never keep up again, So we were in a systems database system. We say, okay, we can replicate. But the problem we have, if the replica dies and recovers, it will never catch up. You know what I mean?
Yes. So the use case for this structure often are rely on the fact that you want to pick as fast as possible by an original source of information.
Yeah.
And keep on doing it by allowing some buffering in case the consumer is slowing down. and that's literally the only use case. So you need to size them accordingly in order to be able to catch up, because you know very well your consumer how much it could be delayed. At the same time, you want to keep as most of the data coming from the source. And you want at the same time that the transfer time will be as lowest as possible. A typical use case is HFT is a good use case, because you basically pick ticks out of a network that can deliver hundreds of millions of requests per second, and you want the total order, because the total order is what defines the price that change over time. So in that case, you really want fast transfer, be able to buffer, and you have in-memory consumer. And in my use case for the previous company was exactly similar. It was medical data, in which each data was ordered. They make sense only if a specific order, and I can slow down the source. Because if I slow down source, I lose data. If I lose data, I'm done. And we were
you were not allowed to lose data, right? So you have to...
In my case, no. In my case, I had this. For the medical use case, I couldn't lose data. So we literally have a giant array that was capable of sustaining several seconds of data. So we are talking about 2 gigabytes of array. So basically the maximum size allows by Java. But it was perfectly fine, because in our case, we were really caring to not slow down anything.
I remember Google complained that the index in array, int, is not enough. They would wanted to have long, you remember?
I believe so. In their case, probably it's a good idea. For Java, I don't know, because, for example, we were using a very specific GC implementation that was not scattering the full array in different elements. While in Java, if you allocate something that exceeds the so-called humongous size, you risk it to be scattered in different regions in order to compose the actual overall object. So the problem is that you actually risk to jump from one of these regions to the other in order to get the continuous element. I don't know with arrays. I think not. I think that arrays are contiguous. So.
This is what Valhalla tries to solve, right? So that they will have a contiguous space in memory where you can do.
But I believe that Valhalla definitely will help in order to have a predictable layout in memory. But at the same time, the people shouldn't forget that the GC are the way by which GC chase and compact object and the which they are allocated often make the compaction happen in a very subtle way. So maybe you have a reference to another element, but since they have been allocated all together, or they're always referenced all together, the GC compaction will keep them near to each other. The problem is that you still have a jump, while when a pointer chase thing, but with the properly completely laid out things in memory, you don't have any jumping, just you go straight. So it's definitely better. But at the same time, GCs make a decent job already to make the memory laid out decently, even if it's Java.
So your problem was simple. So you had 400 million messages per second incoming from the network, and you had to pass them over to something else, and you need a data structure which produces no waste. The order should be predictable and should scale well. It means it should not scale well. It should be able to process the 400 millions per second. This was the requirement, right?
And exactly. Under contention, we were okay to have less. Because the problem is that there is no way, unless you have different queues, actually. So you have one queue for source and you aggregate the results independently. There is no way you can achieve that speed. Because even the XAD, the implementation that I made, maybe is 10 times better than pretty much any queues that I know about under contention, but it's still not so fast. That speed comes from the single producer, single consumer implementation in JCTools, and it's peculiar when you don't have contention. So you have
but you always
producer.
have contention on the such load, or you never have. I mean, there's a high.
Depends if among producer or
Yeah.
producer versus consumer. When I say no contention, I mean producer versus consumer.
Mhm.
While I say good performance under contention, I mean among different producer. So you can have different producer that they all try to hammer the same queue, and
Okay.
you okay.
Okay.
Yeah, right. Effectively, there are different roles, parties involved when it comes to queues. So yes, the most of the algorithm, unless you are using the one from the Java toolkit, have a splitted behavior when it comes to be producer and consumer. Clearly, there are cases in which the contention still can happen between consumer and producer, depending how you implemented it. I'm talking very high level for something that in my mind is fairly low level. So to make it simpler,
two network threads are reading from network for two sockets, and they're writing to the same queue, which is singleton. And on the other side, we have two threads which reading from the same queue and writing in and doing some calculations. Right, one thread is interested in rolling average over 5 minutes, and the other one does total count or whatever.
Yeah. So in these cases, for example, let's say that you fit a case of a multi-producer and single consumer, no? In which you basically drain from different sources, you put more than one thread against the same queue, and you have a single consumer that aggregate results and publish elsewhere. When you are in this scenario, there are not many ways in which you can go very fast because of contention. And it actually depends by the chance that contention happen between producers. So if you have these two producers that are literally keep on hammering the queues, it's very likely that the queue employs some compare and set or get and set or whatever mechanism to coordinate between the two offer in order to make one of them to proceed, the other to retry. No? That's with the normal lock-free implementation for queues. If you are smarter, you can have a mesh of different queues. So you can decide to, like a long adder, to distribute the contention by employing two multi-producer single consumer queues and deciding which one to pick basic or some XOR or hashing mechanism. So you know that the right thread always pick the right queue. And in that case, the cost shift on the consumer side that have to interleave between polling two different
almost
queues.
like a join, right? Between two
like queues. A join, but you would lose the so-called total ordering, because if there is an happens before between the two producer, there's not being respected on the order by which the consumer is going to pick between the two queues. So sometimes in these cases, you would like to use a single structure that does it right. I created the algorithm of the MPSCX add unbounded array queue that is a bit weird, because in x86 there is an instruction called xadd that perform a sort of weight-free increment of a sequence. And I'm using this sequence in order to decide the position in which the actual element should be put. So I split as we said before, I increased the state space by having two separate operations that represented the actual offer. And the offer has become increase monotonically this sequence by using xadd, that is weight-free. You got a reservation, let's say ID, and this reservation ID map in a very unique position in a linked list of array chunk. Based on that, I'm able to find the right position and just place the element there. So it's two states. One state is increasing the sequence, and the other is placing the element. So the real presence of element happen when you place the element in the slot, actually. But you reserve the space for it earlier. No? In this scenario, you are bound in terms of the cost of contention between producer based on how good X had work for the specific architecture. So that specific queue has been implemented in order to leverage what x86 is able to deliver.
Because the sequence increaser is almost like a lock, right? Because it you can place it in the array. This is lock free, but you have exactly know where you can do this, and the decision is in your XAdd operation.
Exactly.
And there was almost like a lock or the decision, where to put it, and this has to be fast.
Exactly. And the idea behind this queue that I implemented for JCTools is coming from another product of a much bigger, more complex product that is called Heron, implemented by Martin Thompson, in which he created a log buffer. And this log buffer is actually a transactional log, let's say. And this transactional log works exactly like that. So it's using XAdd to decide in which offset of a sort of a giant array placed the entries. And it split into a operation, the actual setting an element or placing an element into the queue. The real difference is that the one made by Martin doesn't have to respect the queues because it's a transactional log, so it has its own API in order to be used, and even the linearization of a poll and is empty and offer doesn't have to be respected. While in my case, since I'm bound to implement something that can work well with the queues, I had to think about it as well. And not only, because the other thing is that I wanted to have a weight-free guarantees or make progress. But let's say that you have linked chunks which form the actual queue. No? These linked chunks are made of arrays in which the last element is a jump to a next chunk. What happened? You would like to be able, without any locks, if you are two producers that are be reserved to work on different chunks, to still be able to append to a single data structure the chunks in a way that they don't slow down each other's. They should help each other's. So one of the name that I gave to the data structure initially was a progressive queues, because I implemented a cooperative algorithm in order to make that if one of the two producers fail to append the chunk, he knows for sure that another producer has made some progress. So even if he's not able to make progress, another one is helping him. And if that happens, you know that you can actually compute the number of attempt maximum that you need in order to make your offer to complete. Because without having the real chunk, you have no guarantee that you cannot place the element in the slot. So, and that's actually a queue that is within JCTools and has been benchmarked in many different products.
It's similar to concurrent hash map. They also have regions, right? Which were thread, I think.
Yes, but they are not protected.
No, but from the idea.
Yes, that idea is another idea that is coming. So my implementation is like Frankenstein. It takes good idea from different other data structure. This idea was coming actually from Nissan itself, because previously in Akka, if I remember correctly, they needed an implementation for the mailbox. And since the mailbox is supposed to be unbounded, but they still wanted to leverage the beauty of having to deal with arrays, Nissan created an algorithm in which he was linking arrays. So you amortize the cost of creating new chunks because you create just a full-blown array. And if you are capable to remain in the same array with the producer and consumer, you don't need to allocate a new more. But if something happens in which you exceed the required capacity, you jump in another array. And in that way, you still have this contiguity of memory in a laid out memory that you would expect to have decent performance. So, and
but it wouldn't work. Another approach, I'm just asking, just because I'm curious. let's say you have a giant array, so you can pre-allocate, the biggest array available, and then you add a decision maker. Could, if it's fast enough, could be exposed to multiple threads, and you just decide where to put the index. This would also work, right?
Depends, because let's say that you have this giant array.
Yeah.
Eventually, you will go out of the array.
Yeah, but this
what happened there?
Yeah,
exactly.
But
the point is that you need to eventually to get back.
Yeah.
Get back. Maybe there is already an element there. So what we are supposed to do if there is an element? So and that's why having an API like Qsa doesn't help you to seek the maximum performance, because you are bound to specific behavior. So in this case,
but you could hide your decision maker behind a queue interface.
But if you do it, you will add a loop. So, for example, since you have exceeded the capacity and you don't find any slot, you return false only if it doesn't fit the capacity.
Okay.
But here, you are not saying that you have no capacity. You just say that that specific slot is occupied. So what you can do is to loop until you find the proper place. And how you can prove how much you can loop.
Okay, this is not predictable. Yeah.
That's not predictable. Exactly.
But the consumers, if they read the message, is the message going to be deleted?
Depends. In queues, yes.
Yeah.
In queues is always a disruptive operation. So poll should reduce the size of a queue.
Exactly. So then I mean, if the giant array is full, it means actually an exception. It cannot happen, because it would mean.
But how do you know that's full? Because if the full or empty, if you have an additional variable that say the size, that has to be incremented as well.
Okay. You are far lower than I. I still thought in Java you are on assembly level. So this is.
You require additional.
You're right.
State element. This state element need to all be coordinated, but since you are tied to deliver that sites is empty, poll, offer, deliver a consistent behavior, you cannot make it so very weak the way.
So now I understood what you actually invented, because I thought what you actually did, but what you did is there was in my world it would be no single point of failure, and in your it would be translated no single point of calculation, right? So your contention free means that that the threads don't access a common variable, because if we had a common variable, it would be already contention, and if on Java, in my higher level world, so if we access an int or long, I just access the int. For me, it's not contention. Contention starts with methods, But in your world, accessing an variable, let's say a long, is already problematic. It's already contention, right?
Exactly. The idea is that everything is for the sake of make progress.
Yeah.
In any change of state in which you are basically competing against another party, that competition requires several steps in order to be solved and make a decision. And the decision is what makes the progress to happen. In that case, you would like to design always an algorithm that make a decision or globally visible, or if not globally visible, you need each individual parties to benefit, even if they lose the chance to do something. If you are cooperative in most of your algorithm, or you batch this operation, you reduce the amount of time in which you have the contention, because you want to make a overall progress by leaving each individual to make a fair amount of work each other's. Because the other problem is that you can be very biased always, that a thread will receive all the grants in order to do things, but you don't make other to make progress. So your system is not really scalable. Because even if the total scalability is expressed like the sum of the ability of all the parties to make progress, the reality is that is not fairly distributed. And if it's not fairly distributed, it could be a use case, to be honest, but sometimes it is not. You would like everyone to be able to make progress according to the capacity and their needs to do it.
The last question for today. What I don't understand how you access the XAdd operation, which happens to be an Intel low-level instruction from Java?
Because I read the JDK GitHub repository. So the trick is that we actually have access to this kind of intrinsic, let's say, they are actually normal instruction, to be honest. Because in x86, this instruction is called funny name lock xed. Is not a proper lock, but is how these instructions are being prefixed. And is actually the current implementation starting from Java 8 around increment and get of atomic long and atomic integer. So both expose this xed in a very innocent method called increment and get. Funny things, that's exactly why API naming is important. They could have just exposed get and compare and set. And if you think about it, you can implement your own incremental set there, because you can loop and decide if make progress based on the compare set. When you expose a bigger granularity kind of operation like an increment and set, that allows the implementers to make a smarter implementation based on the available actual capability of the underlying hardware. In this case, the underlying replacement is happening in unsafe or actually through intrinsic that actually knows what kind of CPU it is and perform the wise decision to pick the right instruction.
So what you contributed exactly in JCTools, it was like you contributed, what was what I mean? It was not Java source code, not Java source code only, right?
No, there is not Java. No, mostly Java code, I would say.
And what and also DLLs, or what you did, or
and we have the code generation part. I recently contributed.
You meant the code generation means not the.
This is in Java.
Yeah,
it's in Java. Yeah, it's all in Java. So we do have a plugin in which when you implement a specific queue, and you instruct this code generation part to regenerate a specific source, you pick one implementation, it translated in a way that could produce the new flavor of queues that you need. Based on the different flavor we expose. So we have an atomic variant instead of using unsafe, because in Android, maybe you don't have access to unsafe. In the future, when we will move from unsafe to varendal, it's very likely that we will create a new code generation part that allows to have it. We have another part made by Nitsan, in which we decide how to pad the shared counters and produce queues that have a padding or not. And that part is everything in Java. So this is one of the parts in which I contributed. The other parts are mostly fixes of existing queues and the two flavors of queues that I created.
But when JCTools interacts with the instruction set is mostly with unsafe, right? Nothing else.
Right. We have unsafe as the base implementation and the atomic variant. So you can use
increment and get. I mean, you just the stock increment and get from.
Yeah, I just use atomic long. Actually, not atomic long, because in order to have a bit more control about padding, that is not trivial, because it's very tied by how the hotspot machine decided to pad element. If you use native image, you are done, because native image try to get which field are accessed or not, and the native image delete this field if they are not used. In normal just-in-time hotspot, this doesn't happen. So we have a few tricks in order to make sure that all the counters, so long, are actually at the right distance from each other. In order to access with atomic operation these counters, there is another util coming from the atomic toolkit in Java that is called atomic long field updater. With atomic long field updater, you can define your own class with a private volatile long field, and you just use the updater to interact with that field without having an atomic long. So.
Do you know Mr. Ingo Kegel?
I should see
he created JProfiler. And I think he also uses JCTools internally, because he has to deal with a huge amount of messages. And this is why I also was curious about JCTools. So unfortunately, I have to re-invite you back in some time because we have to talk now about adders. I didn't want to mention them, long adder and so forth. Then atomic longs is also interesting. What happens in Intel, and of course NIO, IO, and what we didn't cover at all. The main use cases of JCTools, like the single consumer, single what to do with it, because what it was interesting as always and unstructured as always because it was interesting to chat with you again. So it was a nice chat.
Thanks.
And what I noticed on GitHub, you are France 1981.
Yeah.
Not France.
I can't change my birth date. It seems so.
Yeah. But I hoped I will find forked France. But you are the France.
Oh, this time was different because I started before being in X, in Twitter, with the GitHub, and that's why. So
okay. Thank you a lot, and people can find you under forked France everywhere. GitHub France 1981.
Yeah.
And what are you doing right now? This week, this month?
Mostly Quarkus performance-related work.
Yeah.
Really.
So because Quarkus now only reaches 390 million transactions per second, and you will go to full 400, right?
Yeah. I mean, probably you got other problem way before, but not because of Quarkus, I would say. But
I don't know whether I told you the story, but I was once hired, to improve the. Not improve. My client was a little bit worried that Quarkus maybe needs some special treatment, and what turned out that Quarkus without any specific configuration was like let's say 10 times, 15 times faster than the peak requirement from my client, and in the reactive mode even 30 times, because in the reactive JDBC driver it almost doubles the scalability. So this was fun actually. So
that's good to know. It's a good feedback actually. So thanks.
Thank you a lot, and see you next time.
See you. Thanks, Adam.